Assalamu alaikum. My ID is 2106134 and I am starting the presentation of our project. Our project is digital stethoscope with noise suppression using FPGA FIR filter. Here's the outline of our project. Our goal was to design a low-cost and high-quality digital stethoscope that can perform a real noise suppression on Xilinx Nexus A700T FPGA board using built-in microphone. 32 tap FIR filter is used to extract clear heartbeat sound. This system can be very useful for healthcare environment. Traditional stethoscopes have several limitations. They cannot store data, have poor noise rejection, and fail to amplify weak sounds. To overcome this issue, our proposed system is based on FPGA that perform real-time filtering and enhances the clarity of important heart sounds. The main challenge is to filter biomedical signals in real time. Heart sounds typically lie between 20 to 150 Hz. Analog filters are faster but suffer from lack of flexibility. So we can use an FPGA which allows parallel processing, ensuring fast performance. Our system processes the signal through a full chain like PDM to PCM conversion, then filtering, and then finally PWM audio out. However, 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 there are several challenges such as converting high frequency PDM data to 16-bit PCM, designing 32-tap FIR filter, and filtering everything within FPGA resource constraints. So that's my part. Thank you.
Assalamu alaikum. My ID is 137. At first, we need to take the raw audio as input. For that, our FPGA board has a built-in ADMP port 1 microphone, which is a PDM microphone, meaning it receives the audio as a pulse density modulated signal. To turn it into computable PCM data, we must decimate it. Decimation is a sort of downsampling. We have considered using a CIC filter to perform this job. Since we want to separate heartbeat from the rest of the audio, we must use a filter. An FIR filter is our best option, as human heartbeat is less than 150 Hz. Passband of 20 to 150 Hz has been considered for the FIR filter. Moreover, the lower cutoff frequency of the filter enables us to eliminate DC noise. We generate a 2.4 MHz clock from the board's 100 MHz clock, and the mic takes PDM data at this frequency. We turn this into sine bits in order to avoid DC offset and feed it into a three-stage CIC filter. It decimates our input data by 64 and we get PCM data of 37.5 kHz. Due to bit growth, the PCM samples increase to 19 bits. We truncate it to 16 bits as audio signals usually have 16-bit samples. After we apply 32 tap Sapphire filter, we get audio of 97.6 kHz sampling frequency. The board's audio output filters it for one less time and we get the PWM audio output. This figure shows the simplified circuit of our project. Here, the CIC and FIR filters have been shown as single blocks, the blue ones. This is the CIC filter block and this one is the FIR filter block. And this is the schematic of our ultimate design. This part is the three-stage CIC filter and this part is the 32 taps FIR filter.
So this is from my part. My ID is 2106158. So as we can see, we have our hardware setup here. We have a pretty simple hardware setup. We have a FPGA board, a stethoscope, and a speaker. Our stethoscope is the one that's capturing the heartbeat sound and giving it as an input to our microphone. And from our audio jack, we are extracting the sound to the speaker and then we are hearing it. So the setup has been shown here in a picture on the right side, and the total demonstration of our project has been shown in the YouTube link below. So let's see how did we implement the whole thing. So we had a heartbeat sound. We captured the heartbeat sound with our PDM it as a PDM format to a microphone, because our FPGA board cannot take the sample or cannot make it a sample value directly from the raw audio. So it basically converts the data into a PDM format fast. So but this PDM format, we cannot work with it. We cannot work with it to to filter it out or to capture the audio or everything else. To do the digital signal processing, we cannot do with our PDM data. So that's why we need to convert it into a PCM signal. So we use a CIC filter to make it PCM, and then we use a FR filter to make it to just filtering out, to filter it out from our main lung sound and other environmental sound, and then we got the clean heartbeat sound with our audio jack output. So let's come our main CIC filter. CIC filter has already been explained uh, by my previous teammates or something. So let me explain it. Let me explain it again. So the CIC filter is nothing but a cascaded integration filter. So we use a third order CIC filter here, and we convert it into a 19 bits PCM signal from our main PDM audio. So this is just a way to make the signal from PDM to PCM. So this was designed by my other teammates, and this is my transfer function that we find here from the CIC filter. And now on my part, that is the FR filter here. So this FR filter was designed with our MATLAB. We know FR filter is nothing but a finite impulse response filter. So for finite impulse response, we need to do the windowing. So we use a Kaiser window and Hamming window to make the filter. And at first we did a lot of tuning. At first we used the Hamming window, and then later on we shifted to a Kaiser window to see which coefficients actually is the best to filter out the audio. And later we found that Hamming window is the best one. So we used a 32 tab as mentioned in our main project criterion. So and we used the built-in MATLAB function for creating these coefficients, and then we multiplied the coefficients of our sample values to filter the audio. So that was my part, and the next thing would be explained by my later teammate. Thank you.
Assalamu alaikum. My ID is 2106138. Now I will present the final part of our project. Starting with design analysis and evaluation, as we can see in this slide, there are two frequency response graphs. The left graph shows the unfiltered signal, which contains a lot of noise, makes it difficult to identify the actual heart sound. The frequency response also shows many unwanted high frequency components. On the right side, the filter signal shows that noise is significantly reduced and the waveform is smoother. Most high frequency components above 115 Hz are removed, while the important low frequency components are preserved because heart sound mainly exists below 115 Hz. Now I will highlight the nobility of our work. Our project implements the full signal chain from PDM microphone to PWM output on a single FPGA, removing the need for extra analog to digital converters and digital to analog converters. It uses 10-bit PWM for high audio resolution and a FIR filter tuned for 20 to 115 Hz sounds to reduce noise. The design is resource efficient, low cost, and suitable for real-time biomedical applications. Now let's look at our design considerations from a public health perspective. If the system works at a low voltage for safety and the volume can be controlled to avoid loud sounds. From an environmental perspective, using a single FPGA reduces the parts and electronic waste. From a societal perspective, the system is low cost and has a simple interface, so even non-expert healthcare can use it easily. While the system is effective, we must also acknowledge certain design limitations. The FPGA uses fixed point arithmetic, which is less precise and has limited resources, so the design cannot be too complex. Simulation don't include real world effects like noise or temperature changes. Testing is subjective, relying on earphones and speaker, and performance can change depending on the microphone placement. Using an analog stethoscope without a proper setup can also add ear noise. This slide shows the contribution of our group members. The team worked on PDM, our input, clock setup, CIC filter, FIR filter, PWM integration, and frequency response analysis. Regarding project management and cost analysis, the total amount of the project cost is 2,300 BDT. Now I will discuss future work. We plan to add adaptive filtering to reduce noise and wireless connectivity for remote monitoring. Additionally, a companion app will allow real-time visualization of heart sounds, and machine learning of FPGA can be used for automatic heart sound classification. The references included in this slide list the sources used for this project. Thank you.